Welcome to the online training Intel Agilex FPGA configuration. My name is Matthias and I will be your instructor for this course. This training is available for desktop viewing as well as in a format compatible with mobile devices. While watching either version, use the controls to navigate on your own or allow the player to autoplay, and feel free to pause at any time. When you are finished, please use the link included in the registration email you were sent to provide us with feedback about the training and ways in which it can be improved. Now let's get started. At the end of this training, you will be familiarized with the Agilex configuration architecture and the Secure Device Manager within Agilex devices. You'll also learn about the various Agilex configuration schemes with the software and hardware involved in enabling these schemes. This training consists of 3 sections. In the first section, we will walk through the Secure Device Manager and configuration architecture. In the second section, we cover details about various configuration schemes, software settings, and hardware necessary for configuration. In the third section, we provide an overview of how remote system update works in Agilex FPGAs. This training involves terms and references commonly used in cryptography and communication protocols. Familiarity with FPGA basics and operation are essential to understanding this configuration training. The first part of this section introduces you to Agilex FPGA configuration architecture. The Secure Device Manager is available in all densities and variants of Agilex FPGA and SoC devices. This block diagram provides an overview of the Agilex configuration architecture, which consists of a Secure Device Manager and a configuration network which connects a mesh of configurable nodes. Depending on which additional hard block is made available to the users via the configuration network, the Agilex device has 3 variants. F-series devices consists of an optimal balance of power and performance, and the option to include a hard processor system. I-series devices consist of high-performance processor interfaces and transceiver rates for bandwidth-intensive applications. M-series devices consist of processor and memory interfaces for compute-intensive, high-bandwidth memory applications. The next part of this section introduces you to the Secure Device Manager. Until the introduction of Stratix 10 FPGAs, configuration logic has been hardwired into state machines. Stratix 10 and Agilex FPGAs changed that approach by dedicating a Secure Device Manager block for FPGA configuration and secure boot process. This slide covers the Secure Device Manager, or SDM, capabilities. The SDM includes all blocks to enable a robust, secure, and fully authenticated configuration scheme. The SDM architecture consists of synchronized processors operating several peripherals, sensors, and cryptographic functional blocks. Let's cover these blocks in some more detail. The power management block consists of a voltage and temperature sensor which enables the Smart VID feature via an external PM-bus voltage regulator. Agilex also introduces the addition of the active low catastrophic trip signal, which is asserted low when the core temperature exceeds 125 degrees Celsius. The AES, SHA, and other crypto accelerator blocks are used for secure configuration to end boot. These hard crypto IP blocks are available to the user after the FPGA enters user mode. This feature will be enabled in a future version of Intel Cortex software. The key vault block provides users for volatile and non-volatile cryptographic key storage. Crypto functions, which utilize keys, require the keys to be stored using a special hardware mechanism to mitigate potential side-channel attacks. The configuration flash controllers enable the active serial configuration scheme via dedicated SDM pins. The Avalon streaming interface configuration scheme is enabled via dual-purpose I/O pins. A fixed PCIe hard IP block within the Agilex device supports configuration via protocol, which is the fastest passive configuration scheme. The configuration data generated by Intel Cortis software is highly compressed to reduce configuration file size, allowing smaller storage memory and faster configuration. This is where the decompression block in the Secure Device Manager comes into picture. This block performs decompression of encrypted and non-encrypted configuration files. This section introduces you to various Intel Agilex FPGA configuration schemes and remote system update. FPGA configuration schemes are classified as active and passive. Active configuration schemes utilize the FPGA as the initiator and the configuring source as the responder memory type. In active configuration, the FPGA automatically begins configuring itself after power-up. As shown in the diagram, in an active configuration scheme, the control signals are initiated by the FPGA and the responder memory responds with the corresponding data. Passive configuration schemes utilize a host as the configuration initiator to configure the responder FPGA device. The initiator host has full control over the responder FPGA device and supplies the control and data signals to the FPGA device. Such an arrangement takes into consideration any back pressure the FPGA may face during configuration file decompression. Several subclassifications exist within active and passive configuration schemes depending upon memory type and communication interface. The MCell pin settings are used to determine the configuration scheme. These pins require a pull-up or pull-down resistor. JTAG configuration scheme overwrites MCell settings and is always available to the user. This table shows the capabilities of the configuration schemes supported by Agilex devices. The first passive configuration scheme we cover is configuration via protocol, also known as CVP, which is performed using 1, 2, 4, 8, or 16 lane PCI Express interfaces, utilizing up to 250 MHz. CVP is performed in two phases, initial phase and update phase. CVP initial configuration dictates the MCell settings for CVP. CVP initial configuration can be carried out using either active serial fast or Avalon streaming. The MCell settings can thus vary for CVP. The second passive configuration method is Avalon streaming, which is available in 8, 16, and 32 bits, and can run up to 125 MHz, allowing a maximum data rate of 4 gigabits per second. The 16 and 32-bit modes utilize dual-purpose I/Os for configuration, whereas the 8-bit mode uses dedicated SDM I/O pins. The 16 and 32 modes use GPIO pins that only support the 1.2 volt I/O standard. The SDM I/O pins require a 1.8 volt power supply. Consequently, you may need a voltage level translation between the FPGA and the external host for some signals to accommodate both power requirements. The last passive configuration scheme is JTAG. As always, you can configure the Intel Agilex device using dedicated JTAG pins. At 30 megabits per second, JTAG is comparatively slow to other configuration methods. JTAG configuration has higher priority over other configuration schemes and is always available irrespective of MCell settings. More details are covered in the JTAG slide. Active serial configuration scheme supports selected third-party QSPI flash memories as well as Intel's EPCQ configuration memory solution. Here we can see a typical configuration via protocol scheme, also known as CVP. A CVP system typically consists of an FPGA, a PCIe host, and a configuration device. CVP configuration scheme supports two modes, namely initialization mode and update mode. Initialization mode consists of two steps. Step 1 consists of configuring the FPGA with a periphery image after power-up using active serial or Avalon streaming configuration scheme. The periphery image simply brings up the PCIe hard IP and helps the FPGA establish a link with the external PCIe host device for further communication. Step 2 of initialization mode consists of initiating a core image through the now established PCIe link. Core image configuration initiates only after the PCIe link training is complete. After the FPGA is fully configured, it enters user mode. Update mode in CVP is used to update the configuration image contained in the FPGA after the FPGA has entered user mode. In user mode, PCIe links are made available for regular PCIe applications. You can use that PCIe link to perform an FPGA core image update. Such core images can be created using Quartus Prime Pro software, provided the core image has identical pin connections as the periphery image. The Avalon streaming interface is a passive configuration scheme, meaning it uses an external host to control transfer of configuration data via an internal or external storage memory into the Agilex device. The host device can be a microprocessor, CPLD, or an FPGA device. The design that controls the configuration process resides in the external host. You can use the Parallel Flash Loader 2 IP core with a MAX2, MAX5, or MAX10 device as the host to read configuration data from the flash device and configure the Agilex device. The Avalon Streaming 32-bit is the fastest Avalon configuration scheme. The scheme also supports 8 and 16-bit data width. The 8-bit configuration scheme uses dedicated pins, whereas the 16 and 32-bit configuration schemes use dual-purpose I/O pins that can be repurposed as general-purpose I/O pins after the FPGA enters user mode. In Agilex, the ready signal for Avalon Streaming 8-bit uses dedicated STM I/O pins, whereas the ready signal for Avalon Streaming 16-bit and 32-bit use general-purpose I/O pins. The pin assignments for these pins can be specified in the dual-purpose pins category in the Device and Pin Options dialog box of Quartus. It is important to note that the nconfig pin is usually pulled up via a 10 kilo ohm resistor for all configuration schemes except Avalon Streaming. JTAG configuration is the most popular configuration scheme, and it is usually the first means of configuration for prototyping or proof of concept designs. It is also used for debug purposes. This slide shows the block diagram for Agilex FPGA configuration using JTAG. JTAG has a higher priority against other configuration means and overrides MCell settings, meaning it will work even if MCell pins are set for another configuration scheme. JTAG configuration is performed not only using the Intel USB download cable 2, but also using the jam player code running on another processor. The pinout for the download cable is shown and is essential to maintain compatibility with the Intel FPGA device. It is important to note that the Intel FPGA does not utilize TRST pin in its JTAG interface. Another consideration when configuring via JTAG is the value of the pull-up and pull-down resistors. These values vary from 1 kiloohm to 10 kiloohms based on the signal integrity performance of the board. Here we can see a block diagram of active serial configuration scheme for Intel Agilex devices. The nconfig pin is tied high via VCC I/O SDM. Connecting nconfig to VCC I/O SDM ensures that the FPGA automatically initiates configuration after all power supplies to the device reach the operating voltage and the power-up sequence is followed. The nStatus, confdone, and initdone signals can be monitored to determine the configuration status or can be left open. The OSC clock 1 is an optional external clock source in addition to the existing internal oscillator. The active serial configuration scheme, set by driving MCell pins to 011, ensures that the Agilex device automatically controls the transfer of configuration data from external storage to the FPGA upon power-up. The by one active serial configuration, also known as SPI, is not supported in Agilex FPGA devices. The Agilex device's active serial configuration has quad data width and supports QSPI mode. Agilex devices consist of an additional fast active serial mode with MCell driven to 001. This setting is usually used for the use of fast periphery image configuration in CVP scheme. The Agilex device configuration process is similar to previous families with a few exceptions. As you can see in the diagram, the Agilex device is first powered up in the proper sequence. Subsequently, when the last power rail reaches operating voltage, a device-wide power-on reset is initiated. After the device exits power-on reset, it enters the Secure Device Manager boot-up state. In this state, the device runs the boot ROM code to set up the SDM. During SDM boot-up state, the device samples the MCell pins to determine the configuration scheme. Bitstream authentication also occurs in this state. After SDM boot-up is complete, the device enters idle mode if nconfig pin is low. Configuration initiates when nconfig pin transitions from low to high. The nconfig pin can therefore be held low to delay the device from configuring from flash. When configuration is complete, the device drives conf_done pin high to indicate it has received all configuration data. It then enters the initialization state where it performs the last configuration steps. The device drives init_done pin high, indicating the device has entered user mode. This is when your design begins functioning. A falling edge on the nconfig pin causes the device to exit user mode, wiping the user design and going into idle state. The SDM then drives nStatus pin low after the device cleaning is done to indicate the SDM is ready to accept new configuration data. An unsuccessful configuration sequence is as follows. 1. The device powers up. 2. The SDM boots up and samples the MCell pins to determine the configuration scheme. 3. The SDM remains in idle state until configuration is initiated by driving nconfig high. 4. If during configuration the device encounters an error, the nStatus pin is pulled low for a minimum of 1 millisecond. 5. nStatus is pulled high, after which the SDM drives nStatus and nconfig low. 6. The device then remains in idle state until a new configuration is triggered by driving nconfig pin high. This configuration timing diagram depicts two events, configuration and reconfiguration. All configuration control signals are active high and are assumed to be in low state initially. After the Agilex device is powered up, as per proper power-up sequence, the SDM boots up and samples the MCell pins to determine the FPGA configuration scheme to be used. Assuming nconfig pin to be held low, the SDM enters idle mode after completing its boot up. When nconfig pin is pulled high, the SDM initiates configuration and signals the start of configuration by driving nStatus pin high. A successful FPGA configuration is indicated by driving the conf_done pin high. The FPGA enters user mode only after init pin goes high, indicating the end of initialization state and the end of configuration. The second event the timing diagram illustrates is the Agilex device reconfiguration. The two key differences between device configuration and reconfiguration are, firstly, the sequence of events after the FPGA is powered up, and secondly, the sequence in which nconfig can be driven to initiate reconfiguration. MCell pins are sampled during SDM boot up. If you switch the MCell settings on the fly, you must power cycle the Agilex device once again for it to sample the new MCell setting. This sequence is not performed during reconfiguration. The device uses the same configuration scheme as the original from PowerUp. Also, the Agilex device reconfiguration follows a certain signaling pattern on nconfig and nstatus pins. Nconfig pin is usually held high throughout normal operation after the configuration is completed. To initiate reconfiguration, the nconfig pin is pulled low, which causes the STM to initiate FPGA device cleaning. The completion of this cleaning activity is indicated by driving nstatus low, as shown in the timing diagram. After nstatus is driven low, you can drive the nconfig pin high to initiate reconfiguration. We'll now discuss the Remote System Update feature in Intel Agilex devices. Remote System Update, also known as RSU, can be used with active or passive FPGA configuration. In active configuration, using RSU and the Mailbox Client Intel FPGA IP, you can write configuration bit streams to the active serial by 4 flash device. The Mailbox Client FPGA IP can then be used to instruct the STM to restart from an updated image. You can store multiple application images and a single factory image in the configuration device. In passive configuration, an external host implements RSU rather than the Agilex device. Refer to this glossary for definitions on some commonly used terms in Remote System Update. Let's take a look at a few of these terms in some more detail. Referring to the firmware term, firmware that runs on the STM implements the following functions: FPGA configuration, voltage regulator configuration, temperature measurement, HPS software load, HPS reset, RSU, read, erase, and program flash memory, and device security, including authentication and encryption. Decision firmware data structure contains the direct-to-factory image pin assignment and PLL settings for the external clock source. This optional clock source drives OSC clock 1. Referring to the factory update image term, the following RSU-related items in the flash can be updated: the factory image, decision firmware, and decision firmware data. RSU using active serial configuration includes the following components: an RSU host design, which can be custom logic, the HPS, or the NEOS 2 processor in the FPGA, one factory image and at least one application image, and flash memory for image storage. Note that the designs that do not use the HPS as the RSU host require the Mailbox Client IP, which sends and receives RSU operation commands and responses. QSPI read and QSPI write are a couple of examples of the Mailbox Client operation commands. Reconfiguration includes the following steps. After the device exits power on reset, the boot ROM loads flash memory from the first valid decision firmware from one of the copies at addresses 0, 512K, 1024K, or 1536K to initialize the STM. The same configuration firmware is present in each one of these locations. This firmware is part of the initial RSU flash image. Step 2. The optional direct-to-factory pin controls whether the STM firmware loads the factory or application image. You can assign the direct-to-factory input to any unused STM pin. The STM loads the application image if you do not assign this pin. Step 3. The configuration pointer block in the flash device maintains a list of pointers to the application images. Step 4. When loading an application image, the STM traverses the pointer block in reverse order. The STM loads the highest priority image. When the image loading completes, the device enters user mode. Step 5. If loading the newest, highest priority image is unsuccessful, the STM tries the next application image from the list. If none of the application images load successfully, the STM loads the factory image. If loading the factory image fails, you can recover by reprogramming the quad SPI flash with the initial RSU flash image using the JTAG interface. Here are the guidelines to follow when implementing Remote System Update. 1. The factory or application image must at least contain a remote system update host controller and the mailbox client IP. You could either use custom logic, the NEOS 2 processor, or the JTAG to Avalon master bridge IP as the remote system update host controller. The remote system update host controller controls the remote system update function by sending commands and receiving responses from the SDM via mailbox client IP. The mailbox client functions as the messenger between the remote system update host and the SDM. It passes the commands to and responses from the SDM. 2. The pre-generated standard remote system update image file should include a factory image and at least one application image. The remote system update image must be programmed into the flash memory. You can use a dummy image to begin developing RSU functionality before the actual application image is complete. The user mode can program additional application images. 3. The remote system update requires you to use active serial by 4 configuration scheme to configure the FPGA with the pre-generated remote system update image. 4. Once the device enters user mode with either the factory or an application image, the remote system update host can perform the following functions. Reconfiguring the device with an application or factory image. This includes from factory to application image or vice versa, and from application image to another application image. The host can also erase the application image, add an application image, or update an application or factory image. This section introduces you to the configuration software settings and programming file types. The device configuration options can be set in the device section of the project settings. To bring up the device settings, you can double-click on the selected device in the project navigator or select device under assignments menu. Alternatively, you can simply bring up the settings from the assignments menu and while there, click the device button. Once you are in the device section of the Quartus Prime Pro software settings, click on the Device and Pin Options button to bring up the Device and Pins dialog box. There you will be able to set the configuration-specific options. If you select the configuration category, you can select the desired configuration scheme. If you want to use the conf_done or init_done output signal, you can select the pins from the signals by clicking on the Configuration Pin Options button. Here, conf_done is set to STM-IO16 using the drop-down box. Next, init_done is set to STM-IO0 again using the drop-down box. Notice that the Secure Device Manager IO16 is red, indicating that it was selected by the previous signal. This table shows the file types supported for Agilex FPGA configuration. The new configuration schemes use existing file types. Hence, there are no new programming files for Intel Agilex devices. Let's go over these file types in some detail. 1. The intended function of SOF or SRAM object files are used to configure FPGA CRAM via JTAG. It is also the source file for RBF, RPD, and POF file types. 2. RBF, or raw binary files, are intended for use with the host when using passive configuration scheme. The host and Agilex device interface can thus be AVST or a CVP root part. 3. POF or programming object file is a file type used to program serial or parallel flash, depending upon the mode being used, active serial or AVST. The POF files are used by Quartus Prime Pro software programmer only. 4. JIC or JTAG indirect configuration is a QSPI memory programming file for active serial configuration using programmer via JTAG. It can be used for CVP as well, if a QSPI device is used to configure the periphery image. When JIC files are used, the FPGA is first configured with the serial flash helper design before programming the flash. In case of Intel Agilex devices, this function is performed by the SDM. 5. RPD, or raw programming data, is a QSPI Flash programming file for active serial configuration when using a third-party programmer to program the QSPI Flash device. For 6, 7, and 8, the JAM, JBC, and SVF file contain JTAG instructions, which allow a third-party host to access the configuration file. The JBC file stores programming data for programming, configuration, verifying, and blank checking one or more devices in a JTAG chain in binary format. JAM files are similar to JBC files, but use ASCII format. This section introduces you to configuration hardware, memory, and relevant IPs. The Intel FPGA USB download cable 2 can be used to download configuration data to Agilex devices and for in-system programming of configuration memories, besides debugging purposes. The explicit error messages displayed on the USB download cable 2, along with signal tap logic analyzer capabilities, make it the first choice for use during prototyping and proof of concept purposes. The USB download cable speed is configurable from 6 to 24 MHz and supports 5V TTL, 3.3V differential LV TTL, and LVCMOS besides single-ended I/O standards ranging from 1.5 to 3.3 volts. The cable speed can be manually varied to meet signal integrity constraints of your board. While there are no new configuration file types, the programmer software has a new ability to program QSPI Flash devices for use in configuration. Active serial configuration for Agilex devices can be implemented using Intel's EPC-QL or a third-party QSPI Flash configuration device. These devices operate at 1.8 volts and support QSPI interface, which is the supported interface type for Agilex devices. These configuration memories are available from 256 megabit to 2 gigabit densities and have an endurance of 100,000 erase or program cycles. This slide briefly explains the commonly used IPs pertaining to Agilex FPGA configuration. The parallel flash loader IP is used most commonly when configuring an Agilex device using the Avalon streaming configuration scheme with an external host. The external Intel FPGA or CPLD host device uses this parallel flash loader IP to provide an interface between itself and the external memory source which contains the configuration data. A JAM player is a C program which runs on a microprocessor or a microcontroller. The JAM player files include configuration data and JTAG commands which are used to emulate appropriate JTAG signals via the processor's GPIO and thus configures the Intel FPGAs. Agilex devices utilize an STM-based mailbox client interface to communicate with an external QSPI Flash configuration device. This client interface acts as a bridge linking the FPGA fabric with the external sources via the SDM. This section provides links to additional reference material for configuration. You can refer to the links in this slide for additional configuration reading and training material. Intel FPGA provides many self-help resources when you need design assistance. For example, there are web pages called landing pages dedicated to specific FPGA technology like transceivers, DSP, OpenCL, and high-speed interfaces. There is also a community forum and hundreds of training courses available just like this one. One last thing. When you registered for this training, a link was sent to you in your confirmation email that links to a short online survey. Please complete the survey to let us know what you think of this training and if you think of ways it can be improved. This concludes this online training. Again, my name is Matthias Berglund. Thank you for your time.